Alright, good afternoon class. My name is Kian.
And I'm Spencer.
And this is our light processor. For our presentation, we have a little outline. First we're going to go over our introduction to light, its designs, our enhancements and our attempt, our diagrams, standard instructions, enhanced instructions, issues, and basically we're just done after that. A little introduction. It is a lightweight and minimalist processor for customers who are pursuing the new trend of a minimalist lifestyle. Not too enhanced or complex, meant to be a potential industry standard. Created with the intention to add enhancements sometime in the future at a time TBD. Our light design. It implements a MIPS instruction set, a microprocessor without interlocked pipelined stages. And it has a multi-cycle data path. Basically means it takes multiple clock cycles to execute a full instruction, this way allowing us to lower the increase the clock frequency. 32-bit instructions and data. We've got a 32 by 32 register file, meaning that we have 32 registers, each 32 bits wide. And we're implementing a Harvard memory architecture. We have separate physical storages and signal pathways for instruction and data, so we can access both simultaneously. And our memory is word addressable. Okay. Here are our enhancements. We added an input to take input from I/O into our data memory and output into our I/O. We have a return interrupt and a set interrupt and a no-op attempt, which we will go over later on. First, I'd like to go over our CPU test module diagram. We just have a reset and a system clock going into it. The system clock is in green, and our reset is in red. So mainly we're going to be focusing on our CPU, but on the outsides we have our I/O memory on the right and data memory on the left. We're going to be able to write and read from I/O memory and the data memory. I'll go ahead and start with the I/O memory first. If we want to read, we'll take the data from the I/O out, and that is accessed by having, we must have the I/O CS and the I/O read on simultaneously, or the I/O read and I/O write on, I/O CS and I/O write on, simultaneously if we want to write to it, which goes into the I/O in. Also similar with the data memory, we have DM out if we want to read from it. We must have DM CS and DM RD, DM read on simultaneously. If we want to write to it, gets sent into DM in, we must have DM CS and DM write on simultaneously. The I/O memory is also capable of sending an interrupt request, denoted by int_r. And that gets sent into our CPU, and we have an interrupt acknowledge which gets sent back out to it. We're going to look more into our CPU in just a moment. So now we have our CPU diagram. Let's go ahead and take a look at what's coming in and out of this. So we have our reset and system clock. We have our interrupt, as previously described, from our I/O memory. We have our interrupt acknowledge coming out. It's kind of hard to see, but there's a blue wire. This is our MCU, which I'll go over in detail in a little bit. We have our DM out if we're reading. We have our signals for reading and writing, as mentioned previously. And we have our IDP out, coming out of our integer data path. So we have three main modules. We have the MCU standing for the MIPS control unit, our instruction unit, and our integer data path. First, I'd like to start out with the instruction unit. This is basically where we're getting all our 32-bit instructions from. It has a PC register, an instruction register, and our instruction memory. Let's say we would like to pull out an instruction from here. It gets pulled out from IR out. It's a 32-bit signal. And some of it gets sent into the integer data path in order to get the S addresses and T addresses, or D address, based on the subset of the instruction word. And the opcode of the IR out gets sent into the MCU, the MIPS control unit. And based on the opcode, we have a ton of control words that basically get sent back to the instruction unit and back to the integer data path to control what's going on. So the MCU is basically a commander. It's got its fingers in both of these, and it's telling it what to do. And it tells it what to do through an implemented state machine. That state machine varies from just a few states to up to 6 on a write back for a load state, for a load of instruction, because it has to access memory. And yeah, so 3 to 6 clock cycles, and in each one of the states, various control words get changed. Coming out of the integer data path, we have most of our computations and our flags. You can see it's sent out over here. And I want to go over our PC register in our instruction unit. The PC register is the program counter. That's where we keep track of where we are. And most of our instructions are going to have a regular PC increment, which increments the PC by 4. Otherwise, we have a PC load or a PC select to select other values to be inputted into PC or added onto PC for a jump or other instructions. And we're going to keep going and look more in depth into the integer data path now. So for our integer data path diagram, we've got 6 main modules, some of them just being regular registers, 5 muxes, an ALU, our reg file over here, and our high-low register. I'm going to go ahead and get started with our register file 32. This is going to be used to select the data. The data is going to come out from the S and T signals, and the address is going to be decided by what is sent into the S and T addresses. The DA out is going to select whether we use D address or T address based on the opcode, and send that in as the D address. The S address is selected with our SP mux out, and the data from the S and T gets sent into our RSRT. It's kind of hard to see here. It's sent into this register, and from here they get sent into our ALU. And our ALU takes in the data as the S data, the T data. This does most of our computations. The opcode is, we get our opcode from our 5-bit FS signal from outside. We also have a shift amount input from outside, if it's a shift arithmetic or a shift logical. We have our CV and Z flags, which come out of the ALU, which are just our status bit flags. And our ALU takes the Y-low 32-bit value, let's say after a computation, and it'll send it into the ALU register up here. And it comes out of the Q ALU and goes into the ALU out. And based on this mux, it can just write back into the D of the register file. This ALU out decides what can get sent back into the register file. And then we also have a T mux out over here, which selects what value of T gets sent into the DT over here, into our RSRT register. So instead of choosing something from a T address register from the reg file 32, we can just go straight into a immediate value or a PC value. And I'm going to go over the high-low register over here. This is used when we have a multiply or divide function. For a multiplication function, we're taking the 64-bit value and splitting them into the high and the low. And for division, it's used as well. And yeah, that's pretty much much it. For our R-type instructions, we have an example format over here. There's our 32-bit word length. The opcodes for an R-type are always going to be 0x00. The function is actually going to denote what variant of the R-type instruction it is. So IR5:0. Shift amount is used if we have shifts arithmetic or shifts logical. R's are special because they have an RD register, which is basically a destination register denoted by the first R in the instruction. And then the next one is the RS and the next one is the RT. So these two last ones are actually the source registers, and based on wherever the R-type instruction is, the result gets written into RD. Next, we have an I-type instruction. For this, we actually do use the opcodes, so bits 31 to 26 denote what kind of operation we're going to be doing. Notice how there is no RD in this one. Instead, we just take RS and RT right away. And RT is going to be the register we're going to be writing to. And we're going to have a 16-bit offset or immediate following it right after it. So for this example, we're doing add immediate. We would add whatever is within the register of R0 with the -4 immediate value and write it into R1.
Are you sure about that assembly language syntax? I think that's reversed. I think the MIPS puts RT as the last one, or the leftmost one, if you will.
As it should be here.
So that would be RT gets R1 minus 4. That's the MIPS syntax.
Okay.
Just a little adjustment, yeah.
Okay. And then next we have a J-type instruction. So for this example, we have a jump and a 26-bit address, which in order to do this, we take this 32-bit word and we cut off the first two least significant bits, and after that we count from right to left 26 bits and cut off whatever is left over after that left side. And then we convert that back into hex. We got to convert this to binary first, do what I just said, and then we convert it back into hex after that. And that is our J-type instruction example.
So for one of our enhanced instructions, we have output, and we use output to write to I/O memory. And on the left side, you can see the state, and on the right side, the next state. And the first two states are the same, just fetch and decode, and then first output state, we calculate the effective address of where we want to write to I/O memory. And then the last output state is when we write to I/O memory. And instead of using chip select and write for data memory, we just use the I/O chip select and write. For input, it's the same thing. We read from I/O memory instead of write. First two states are also fetch and decode. The first input state is to calculate the effective address, and then the second input state we use that address of where you want to read data from I/O memory. And then we go to the write back state, which is writing to the register. And we also use the I/O chip selects and I/O reads instead of data memory chip select and data memory read. And this is an example of using input and output. And right here we can see where we're outputting. We're outputting to R16, which is pointed to right here. And each register in our memory is the result of each shift, which is going on in this instruction. And then to confirm that our shifts are working and our outputs and inputs are working, we write back into these 6 registers in a register file. It's just a copy of these contents. For our interrupt handling, we first check for our interrupt enable and our fetch state. Instead of just increasing our PC, we have this check. We can also check for interrupts. And if interrupt acknowledges 0 and our interrupt from hardware, which is INTR, and our interrupt flag, which is PSI, if they're both 1, then we go to interrupt states instead of just going to decode. And then we set interrupt flag in our steady state, and then our return from interrupt states is in our RETI. So for our interrupt states, we have a total of 6 states, so this is the first 3 and this is the last 3. We also, so again in fetch we check for the flags. In our first interrupt state, we pass our stack pointer into RS and we save our current PC into our temporary register. And then we pass the stack pointer into ALU out so we can decrement it later in the future interrupt state. In our third interrupt state, we read the address of our ISR into DN. And in our fourth state is when we decrement as our stack pointer and we load the PC with the address. In our fifth interrupt state is when we push the PC, push our current location onto the stack to return later, and then we also prepare to push our current flags onto the stack. And our last interrupt state is when we push our flags on and we write our stack pointer into our register file. And basically in these states we push our PC that we want to go to and return from, and then we push on our flags onto the stack.
So Spencer, on step 4, it says PC goes into RT. Is that the PC that you put into register 31?
This
Goes
one
into
here?
RT?
Right here?
Yeah, because back in step 3, was it, or 2, you say that the PC goes into RA.
So this was our current PC that we want to save to go back to.
Right. So then at step 4, you say PC goes into RT. So is that, this is for me when I'm actually looking at your project, at that step 4, you're bringing it out of the register file from register 31 into RT? Or are you going directly into RT from the PC?
We're going into RT from the PC.
Why did you put it into RA then in step 1?
Just so we can save it and then we come back to it. When we
But
just
we're
jump
saving
back.
it on the stack, not the register file, I thought.
Oh.
No, back at step 1, go back there.
Uh-huh.
So you're going to be saving it on the stack, but you put it into RA.
Uh-huh.
So I'm just wondering why.
Because I think we need it to when we come back from the interrupt.
I thought you'd be getting it from the stack, because that's why you're going to push it on the stack when you return from interrupt.
Oh.
See, so like you're storing
Yeah,
it
I
in
see.
2 spots. That's
Mhm.
what I'm.
So I think here we just did an extra step that we didn't really need.
Okay. Save it in 2 spots.
Yeah, so it's an extra.
Okay, that's good. It's clear though what you're doing. It's good.
Yeah. And then so we just save our flags and then we save our PC in our interrupt states. And then from return interrupt, it's just the reverse of what we did in our interrupt states. So we also calculate the effective address of our stack pointer, and we get ready to push our flags in these states, our current flags statuses. And in this one, we don't need our inner flag because it's already on, or it's already set to high. And then this is just a continuation of incrementing back the stack pointer to get back to where we were originally from the interrupt. And then this is just another example of using our return, and instead of using a jump here, we used our return for interrupts. And this is the same shift that we did earlier, and we just save our copies to make sure our returns are working. And then our attempt at no-op, which we didn't really get to test out, we only made a control word for it just to keep ALU out. We just passed ALU back into ALU out, but then we never got to actually test it by making our own memory module to implement this into our design, which we have to finish on later on. For issues, so for some of our issues we had when we were creating our MCU, so we would have a couple of control words that were off. So sometimes we weren't writing data to certain states when we wanted to write data, so it would not write anything at all or write wrong data. And then those cause some problems because then we can't go on to the next instructions, so we had to go back and make sure that we were pulling from the correct registers when we wanted to write to like memory or something. And then we just couldn't create other enhancements because we didn't allocate enough time to work on new stuff besides the base instructions. And that's it.
Okay, good presentation. Thank you guys.